In section 3.4, we introduced the idea of a z-score. So there's another technical sounding word, but what is it? All it is a distance that a data value is, or a data point, if you'd rather call it that. The distance that data point is from the mean. The part where you sort of have to pay attention is that this distance is going to be in terms of the number of standard deviations. So to get a better idea of what we're talking about, let's just look at how we describe distances. Okay, here's me, and here's a tree. And I want to know, how far am I from that tree? Using my fabulous drawing ability here, I don't want to say just that I am 12 from that tree. We never say just 12. We always include a unit. So that unit might be, I'm 12 inches from that tree. Maybe I am 12 miles from that tree. Maybe I'm 12 kilometers from that tree. So distances involve units, and the z-score is going to be a distance where the unit is the standard deviation. Okay, so let's look at the formula for finding a z-score. So if we're doing this with a sample, then our formula is going to look like our data point minus the mean of our sample, which is x bar, divided by the standard deviation of our sample, which is s. If we're finding a z-score using the population values, then that z-score, which sometimes we abbreviate with the letter z, is our data point minus the population mean divided by the population standard deviation. So this is how you find the z-score. Let's look at an example of when we might want to use this. Let's look at an example using the variable IQ. These are actual numbers that come from measuring a lot of IQs. So these actually are parameters. We've got two people. Here's Bob and here's Linda, obviously. And Bob's IQ is 130 and Linda's IQ is 115. We want to know how many standard deviations are they from average. This is a question that is actually a little more useful than it might sound to begin with. So what is that? That's just a z-score. So to figure out the answer to this question, we just need to calculate two z-scores. We'll calculate the z-score for Bob. I'll call that z sub Bob. And we'll calculate the z-score for Linda. We'll call that z sub Linda. So here's Bob's z-score. It's his data point minus the mean divided by the standard deviation. Here's Linda's z-score. It's her data point minus the mean divided by the standard deviation. And so I could say that Bob's IQ is 2 standard deviations above the mean, above average, and Linda's IQ is 1 standard deviation above average. Again, these are just distances. And in this case, it might be pretty easy to see what's going on. But it's useful to know how many standard deviations something is from average. Because in statistics, we're going to be thinking about how the variability of a variable, how its standard deviation affects how unusual a data value is. And knowing how far something is from the mean in terms of the number of standard deviations is going to give us a very good idea of how unusual those data points are. A much better idea than if we just looked at, say, the fact that Bob is 30 points above average. It's more useful to us to know that he's 2 standard deviations above average. And the same thing for Linda. We could say that her IQ is 15 points above average, but it's going to actually be more useful to say that her IQ is 1 standard deviation above average. So both of these numbers right here, this 2 and 1, are both z-scores. So here's an example of a fairly typical wordy problem from this book, for better or for worse. So let's read this. All right, we have the mean height of males 20 years age or older. That is the mean. And furthermore, it looks like it is a population mean because they don't say this came from a sample. And the standard deviation for these males here is 2.8. So that is a population standard deviation. That's sigma. And then we've also got females' heights, and their mean is a little lower, and their standard deviation is not the same. It's 2.7. So we have a lot of numbers here, so it might be a good idea to sort them out a bit. We basically have two populations. So what are we trying to do? We're trying to see who is relatively taller. Kevin Garnett, who is an NBA basketball player, who is 83 inches tall, or Candice Parker, who is also a professional basketball player, who is 76 inches tall. And by relatively taller, they mean compared to their gender. So we're going to be comparing Kevin Garnett to males and Candice Parker to females. So I'm just going to take a second and organize these numbers really quickly. So you can see taking some time to organize this data in a table like this is going to be a lot nicer than having to go through all these words and figure out what all this stuff is representing. I highly recommend with a word problem, pull these numbers out and write a little table like this. So, okay, we want to know who is relatively taller. Obviously, who is taller is a boring question. Kevin Garnett is taller here. Who is relatively taller is going to depend on the distribution of their gender. So because their genders, males and females, have different distributions of their heights, we want to account for the differences in these distributions. And so to do that, we're going to put their heights on equal playing fields by using z-scores. So we're going to find the z-score for Kevin Garnett's height, and we're going to find the z-score for Candice Parker's height, and that is going to essentially be a more equal playing field to compare who is taller. Here we go. His data value, which is 83, minus the mean, which is 69.1, because he's a male, I want to use the mean for males, divided by the standard deviation for males. And when I do that, I get 4.96. That's his z-score. That tells me Kevin Garnett is 4.96 standard deviations above average. Whereas Candice Parker, same thing, we're going to use her data value, her height, but now we're going to use the mean of females, which is 63.7, divided by the standard deviation for females, which is 2.7. And when we do that, we get 4.56. So she is 4.56 standard deviations above average. They're both very tall people. But now that we've found the z-scores, we've essentially found a way to compare who is taller relative to their gender. Kevin Garnett is almost 5 standard deviations above average, whereas Candice Parker is only 4.56 standard deviations above average. It turns out that's still incredibly tall. So even when accounting for the fact that males are taller than females on average, Kevin Garnett is still relatively taller. Who wins this battle? Kevin Garnett. Why does he win? Because his z-score is higher than Candice Parker's. He is more standard deviations above average. So when we want to compare two numbers, like 83 inches and 76 inches, we need to put them on equal playing fields if they come from different distributions.